Now that we're talking about matrix operations, and now that we've brought up matrix multiplication, we need to talk about the inverse of a matrix. So specifically, we want to talk about the multiplicative inverse of a matrix. So when we talk about the inverse of a matrix, we're specifically referring to the multiplicative inverse. So let's recall some things about that we're going to need to develop this. So recall, for real numbers, the multiplicative inverse is a reciprocal. For real numbers, the multiplicative inverse is a reciprocal. So 5 times 1/5 is equal to 1. So 5 is a number, 1/5 is the reciprocal of 5. When we multiply them, we get 1, which is the multiplicative identity. So 1 is the multiplicative identity. An identity element is an element that doesn't do anything under the operation. 1 times what you start with is just what you started with. So an identity element means it doesn't do anything under the operation. One times x is x. So that's what makes it a multiplicative identity. When we multiply by 1, nothing happens. On a related note, 0 is the additive identity. So zero plus x is x plus 0 is just x. 0 doesn't do anything when we add it. So 0 is the additive identity, because 0 does nothing under addition. 1 is the multiplicative identity, because 1 doesn't do anything under multiplication. So for real numbers, multiplicative inverses are called reciprocals. You just flip them over. Since additive identities have come up, additive inverses are opposites. So 5 plus a negative 5 is equal to 0. An inverse is what gets you to the identity. So an inverse is what gets you to the identity. An inverse gets you to the identity. So the additive inverse of 5 is the opposite of 5, negative 5, because when I add 5 and negative 5, I come up with the additive identity, which is 0. So that's a lot of structural namings of things, but we need to have this context so that we can see how matrix multiplication is different, because matrix multiplication is not like other multiplications. Hashtag not like other multiplications. An interesting and relative and related fact is we should note that the additive identity does not have a multiplicative inverse. I guess this is the I've used up all my colors. And this is true in general. The additive identity does not have a multiplicative inverse. Because when I multiply by 0, I always get 0. I can't multiply 0 by anything and come up with 1. So the additive identity does not have a multiplicative inverse. 0 has no reciprocal. All right, that's some context. Because we're talking about multiplication, we need to understand about identities and inverses, multiplicative inverses. Let's start by writing down the inverse of a square. So let's back up a second. So for matrices, we're going to note, we're first just going to accept that only square matrices are invertible. Right now, I'm just going to drop this as an edict. Only square matrices can be invertible. The multiplicative identity, the identity matrix, is going to be a square matrix with 1s on the main diagonal and 0s elsewhere. So I'm going to call it I sub n, the n by n identity matrix has 1s on the main diagonal and 0s elsewhere. So I2, the 2 by 2 identity matrix will be 1, 0, 0, 1. I3, the 3 by 3 identity matrix will be 1, 0, 0, 0, 1, 0, 0, 0, 1. And so on. Now these get to be the identity matrices because if I multiply an identity matrix by any other matrix, it shouldn't change anything. So let's try that. Let's suppose that A is equal to 1, 2, negative 3, 5. If I multiply I times A, well, I guess I'm doing AI times first. So I take 1, 2, negative 3, 5, and multiply that by 1, 0, 0, 1. I'm going to get 1 times 0 plus minus 3 times 0. Sorry, 1 times 1 minus 3 times 0. So 1 times 1 minus 3 times 0. Then I'll multiply the first row by the second column. I get 1 times 0 minus 3 times 1. Then I'll do the second row times the first column. So 2 times 1 plus 5 times 0. And then 2 times 0 plus 5 times 1. And we end up with what we started. 1, 2, negative 3, 5. So this first column of ones, 1, 0, this 1, 0 column grabs one copy of the first column of A and 0 copies of the second column of A, and that's just going to give us the first column of A. Similarly, the second column of the identity matrix, 0, 1, is going to grab 0 copies of the first column of A plus 1 copy of the second column of A. Here's the 0 wiping out the first column of A, and here's the 1 grabbing 1 copy of the second column of A. If I put the identity matrix on the other side, I should also come up with A. So let's calculate IA. So now, if we think in terms of combinations, this 1, 2 column of A is going to grab 1 copy of the first column of the identity and 2 copies of the second column of the identity. And that's just going to give us 1, 2. So let's see that in action. I'll do 1 times 1 plus 0 times 2. 1 times 1 plus 0 times 2. Then I'll multiply the first row times the second column, so I'll have 1 times negative 3 plus 0 times 5. And I'll do the second row times the first column, I'll have 0 times 1 plus 1 times 2. And I'll do the second row times the second column, I'll have 0 times negative 3 plus 1, 0 times negative 3 plus 1 times 5. I did this one backwards, didn't I? No, I didn't. Plus 1 times 5. So I still get 1, 2, negative 3, 5. So in this case, A times I was equal to I times A was equal to A. I is the identity matrix, because multiplication by I doesn't do anything. That's what a multiplicative identity does. When we multiply by the multiplicative identity, nothing should happen. So let's talk about how to find the inverse of a matrix. Actually, I keep wanting to do that, and I keep backing away from that. So the important thing to note is that not all square matrices have an inverse. Not all square matrices are invertible. So if we compare this to what we know about the multiplicative inverse for real numbers, only 0 has this property. So we know that 0 does not have a multiplicative inverse. But in the case of matrix multiplication, there are a lot of matrices that are not invertible. So there are a lot of non-zero square matrices that don't have a multiplicative inverse. That's what makes this weird. For real numbers, there's only one real number that doesn't have a multiplicative inverse. So this is strange that not all square matrices are invertible, because only one real number does not have a multiplicative inverse, and that's 0. 0 doesn't have a reciprocal. But there are lots of square matrices that don't have reciprocals or inverses. So let's talk about finding the inverse. Or do I want to talk about the result of this? So because not all square matrices are invertible, this has some consequences. So if I have AB equal to AC, this does not mean that B equals C. That's crazy. We can't just cancel the A because A might not be invertible. That's the way we need to think about it. We can't just cancel the A because A might not be invertible. This is one of the strangest things that we have to deal with when we're dealing with matrices. We can't just cancel the A because A might not be invertible. This is one of the legacies of our kind of lackadaisical approach to teaching algebra. Because we talk about if 5x equals 10, we talk about canceling a 5. But what we're doing is we're dividing both sides by 5. So if this same statement is true in real numbers. So the same thing is true in real numbers, but since there's only one number that breaks it, we just let that go. So if xy is equal to xz, that doesn't really mean that y is equal to z, but the only time it doesn't work is when x is 0. So xy equals xz does not imply y equals z. If x is not 0, then xy equals xz implies that y equals z. But a lot of times when we're doing algebra, we leave that part off. If x is not 0, then xy equals xz means that y is equal to z, because I could divide by x. But in general, xy equals xz doesn't mean that y is equal to z. So the reason that we can't just cancel the x here is that x might be 0. So the reason that we can't just cancel an a here is that a might not be invertible. So what we're trying to associate is not matrices that are not invertible acting like the number 0 in a multiplication. So that's an important consequence to not all square matrices being invertible. We can't just like cancel a matrix. So let's find a matrix. Find the inverse of a matrix. Let's start with a 2 by 2 case. So first, I need to introduce a matrix inverse notation. So we put a to the -1 when we want for it to be, when we want to talk about the inverse of a matrix. So A is going to be this matrix A, B, C, D by rows. then the inverse of a matrix is going to be 1 over AD minus BC as a scalar. So we take the scalar AD minus BC, the reciprocal of that, and then we can just rearrange the rest of it. So if we have a 2 by 2 matrix, then here's how we find the inverse. If AD minus BC is not 0. If AD minus BC is equal to 0, then A is not invertible. Another word for not invertible is singular. So this is nice because all we have to do is remember how to do this. So for example, if A is equal to 1, 3, 2, 4, then A inverse is 1 over 1 times 4 minus 3 times 2. We flip the main diagonal for 1 and change the signs off the diagonal, negative 3, negative 2. So we get 1, 4 minus, so negative 1/2. And it should be that if we multiply these matrices, A times A inverse, we should get the identity. And if we multiply A inverse times A, we should get the identity. Another way to find the inverse of a matrix is to use your machine. So I have the matrix, what did I put? 1, 3, 2, 4. 1, 3, 2, 4. And we're going to use the same notation. We're going to use the to the minus 1 button. So we do to the minus 1. That's say find in the context of matrices, this will be saying find the inverse of the matrix. And that's what we got. Negative 2, 1, 1.5, negative 0.5. So that's number 1, how to find the inverse of a matrix. There are formulas for larger matrices, but to find the inverse of a matrix if it's 3 by 3, but you do not want to use them. There's a row operation for finding the inverse of a matrix that you only want to use if you are specifically called upon to find the inverse of a matrix. If you can avoid finding the inverse of a matrix, then you should avoid finding the inverse of a matrix. That is to say, you should only find the inverse of a matrix if you are specifically told to find the inverse of a matrix. So, with that in mind, if A is invertible, then the row operations that transform A into the identity matrix the same row operations that turn A into the identity matrix will turn the identity matrix into A inverse. I've said a lot by saying this. If you have an invertible matrix, then it is row equivalent to the identity matrix. And moreover, the row operations that turn A into the identity turn the identity into A inverse. So what this means is that if we make an augmented matrix AI, this will be row equivalent to the identity matrix and A inverse. So here we are saying that that an invertible matrix is row equivalent to the identity matrix, and the row operations that turn the invertible matrix A into the identity matrix will turn the identity matrix into the inverse. Now keep in mind, we're only going to use this if we need to find the inverse of the matrix because we've been directed to do so. If we're trying to solve a problem, we don't want to grab the inverse of a matrix and start multiplying the inverse by a bunch of stuff. There are better ways to solve problems where we can avoid this process. Mostly because this process is going to be very mechanically intensive. So, and it might not really tell us anything more than we can get otherwise. All right. So those are the things to get you started on completing the homework from 2.1, 2.2, and 2.3, matrix operations. Let's pause the video here and talk about the stuff at the end of chapter 2, which is subspaces. All right, so let's pause the video here, and then we'll come back and talk about subspaces.